Hello everyone, myself Monishan Gowda. I'm currently studying in Sri Venkateswara College of Engineering, pursuing Electronics and Communications. Today I'm gonna make a video on the subject Electronic Principles and Circuits, and today's topic is designing high fidelity audio amplifiers using MOSFETs. Welcome to this comprehensive guide on designing high fidelity audio amplifiers using MOSFET transistors. We will dwell into the fundamentals, explore the advantages of MOSFETs in audio applications, and examine crucial design considerations for achieving exceptional audio fidelity. Fundamentals of MOSFET transistors. Structure and operation. MOSFETs, metal oxide semiconductor field effect transistors, are three-terminal devices that control the flow of current between the source and drain terminals using an electric field applied to the gate. Types of MOSFETs. There are two main types, N-channel and P-channel MOSFETs, distinguished by the type of charge carriers responsible for current flow. N-channel MOSFETs use electrons, while P-channel MOSFETs use holes. Advantages in audio applications. MOSFETs offer several advantages in audio amplifier design, including high input impedance, low output impedance, and excellent linearity, contributing to high fidelity audio reproduction. Key parameters. Important parameters for audio amplifier design including transconduction, drain current, and gate source voltage, which determine the amplification characteristics. Advantages of MOSFETs based amplifier design. High input impedance. MOSFETs have a very high input impedance, meaning they draw very little current from the signal source. This minimizes loading effects and preserves the signal integrity. Low output impedance. MOSFETs have a low output impedance, allowing them to drive a wide range of loads without significant voltage drops. This ensures efficient power transfer and accurate signal reproduction. Excellent linearity. MOSFETs exhibit excellent linearity over a wide operating range, minimizing distortion and ensuring faithful reproduction of the audio signal. Amplifier classes A, AB, and B. Class A. Class A amplifiers operate in a linear region where the output transistor conducts for the entire input cycle. They offer low distortion but suffer from low efficiency and high power consumption. Class AB. Class AB amplifiers operate between Class A and Class B, offering a compromise between efficiency and linearity. They achieve higher efficiency than Class A but introduce some distortion. Class B. Class B amplifiers operate in a push-pull configuration, where each transistor conducts for half of the input cycle. They offer high efficiency but introduce crossover distortion at the zero crossing point. Biasing and quiescent current considerations. Setting the operating point. Biasing involves setting the quiescent current and operating voltage to ensure the amplifier operates in its linear region and avoids distortion. Voltage dividers. Voltage dividers are used to create stable reference voltages for biasing, ensuring that the transistor operates within its specified range. Feedback resistors. Feedback resistors are employed to stabilize the operating point and compensate for variations in transistor parameters, enhancing the amplifier's reliability. Quiescent current optimization. The quiescent current should be optimized to achieve a balance between distortion, efficiency, and thermal performance. This involves considering factors like power dissipation and heat management. Gain and output power requirements. Gain, amplification factor, determines the overall amplification of the amplifier, enhancing the volume and power output. Output power, maximizing power delivery, specializes the maximum power the amplifier can deliver to the speaker load, influencing the loudness and dynamic range. Bandwidth, frequency range, defines the range of frequencies the amplifier can reproduce faithfully, ensuring accurate reproduction of the entire audio spectrum. Distortion and linearity analysis. Harmonic distortion. Harmonic distortion arises when the amplifier produces multiple of the fundamental frequency, causing unwanted coloration and degradation of the audio signal. Intermodulation distortion. Intermodulation distortion occurs when the multiple input frequencies interact within the amplifier, creating unwanted combination tones that affect audio clarity and fidelity. Linearity measurement. Linearity is measured using techniques such as THD, total harmonic distortion, and IMD, intermodulation distortion, which quantify the amount of distortion introduced by the amplifier. Minimizing distortion. To minimize distortion, careful design choices are essential, including selecting high quality components, ensuring proper biasing, and implementing feedback mechanisms. Power supply and regulation. Transformer. The transformer steps down the AC mains voltage to a suitable level for the amplifier circuit, providing isolation and ensuring safety. Rectifier. The rectifier converts the AC voltage to DC, creating a pulsating DC waveform. Diodes are used to achieve this conversion. Filter capacitors. Filter capacitors smooth out the pulsating DC waveform, providing a stable DC voltage for the amplifier circuits. Voltage regulator. Voltage regulator maintains a stable output voltage despite fluctuations in the input voltage or load current, ensuring constant power delivery to the amplifier. Thermal management and heat sinking. Power dissipation. Power dissipation is a significant consideration in amplifier design, especially for high power applications. The output transistors generate heat due to their current flow and voltage drops. Heat sinks. Heat sinks are essential for dissipating heat from the transistors, preventing overheating and potential damage. They provide a larger surface area for heat transfer to the surrounding air. Thermal resistance. Thermal resistance is a measure of the resistance of heat flow. Lower thermal resistance indicates more efficient heat transfer. Choosing heat sinks with lower thermal resistance is crucial for effective cooling. Thermal protection. Thermal protection circuits are often incorporated to shut down the amplifier in case of excessive heat buildup, preventing damage to the components. Conclusion and design considerations. Designing high fidelity audio amplifiers using MOSFET transistors require thorough understanding of the underlying principles, careful selections of components, and attention to detail throughout the design process. By considering factors such as biasing, gain, distortion, power supply, and thermal management, audio enthusiasts and engineers can create amplifiers that faithfully reproduce the norms of music and deliver an immersive listening experience.